What I'm going to do is frame up a lot of the conversation today using an energy client, or really energy as a vehicle. But this really applies, to all kinds of different verticals. This is really just a vehicle for the dialogue. So I don't want to get too hung up on that. And what I'll be spending a lot of time on is on the machine learning side of things, how that integrates with IoT devices, some of the challenges we have there, but really focusing on the AI and the machine learning. Art is going to spend a lot of time unpacking IoT and also bringing up some new technologies that can make our lives easier with machine learning and how that comes together. And then Eric's going to bring it all home for us. How do I get this out there in the field? How do I deploy this? How do I keep on making sure that these machine learning or AI models are fresh and adding business value to us? So again, just to kind of continue or frame up our dialogue right here, we've got our hypothetical energy company right here who is producing electricity. So they've got the generation side of things, we've got the distribution side of things, and then we've got our consumers that are actually consuming all of that energy, using the electricity, using the business. That's great. And as we're going and pulling all this information together, we want to ask some really interesting questions that's going to make our business different. Add some business value. What can we do once we start pulling in line of business, ERP, and also IoT devices into this? What do IoT devices give us that change some of those questions we can ask? I kind of go from, I'd say capability maturity model, from simpler to more sophisticated. So I'd say the first thing we have here are really just great analytics, which is business intelligence if we're talking 5 years ago. So amazing visibility into your data, where you can ask some of these rich questions, what about if I am making a giant capital investment? How does that get all the way back down to my customers? How is the revenue we're collecting from those come all the way back to that capital investment, so we know when we've got that return? When have we met that? What's the profitability going to be ultimately? So that's some pretty interesting visibility all the way through that. Then we get into the predictive side of things. If we have these great IoT devices, all right, that are operating at the generation side, at the transmission side of things, there's some interesting scenario that brings up, all right? If the weather changes, it gets warmer, maybe you want to change how much we're generating, how much power we're putting out. If there's a transmission problem, do I want to redirect that to different clients, different customers, homeowners, things like that? All of this is going to help us with managing that ultimately what our product is, and that whole pipeline that we're working through. And then, of course, what-if scenarios. This is where we can take those predictive models that we've generated and just plug in different scenarios for investments, so on and so forth, and see how that might shape out. What if there's a change in the market? What if there's another, we have more natural, weather events like we've had this year so far? What if next year's like that? How is that going to play out? So some interesting things we can do, and it's not just us getting that information with a gut feeling, but we've got data to back it up. So now when we're going to actually make these requests for new capital investments, or to strengthen our supply chain or our transmission side of things, we've got some numbers that will help us get there. Now we really want to focus on the IoT side of things. So when we're dealing with IoT, we may have all these individual sensors at these various areas, and they're going to be generating all kinds of data for us. So these IoT devices can be pretty chatty as far as what they're generating for us. So we may have something here where, on this side of it, on the generation side, we've got our turbines, and we'll take a look at that in a little bit, that are generating our power. Is there vibration on those things? We want to record all of that. On the transmission side of things, again, we want to understand what our substations look like. And as all of these things are functioning, we've got to have a funnel to capture this data. We'll get into the data volumes. We can deal with these, but essentially, this is just really a data consumption platform. So essentially, we're dealing with big data, streaming analytics, and then we're also dealing with batch, two sides of that. Now, we don't just want to have our information coming in from the IoT devices. We want to bring that together with our line of business system as well. So that's our ERP. So we've got the financial models that come back to it. And also, for the work management, Power Plan is a popular package inside of energy companies. So we happen to have that there. Depends on what your industry is. It could be all of those. Essentially, we're bringing this data together in an aggregated fashion so we can plug in an analytics module. Now, when we do our analytics, oftentimes it's up in the cloud, but due to certain client needs, we have to bring that down on premise. And then also we need to deploy that perhaps potentially to different territories. We've mostly worked with Google TensorFlow, Microsoft Cognitive Toolkit, or Azure ML. All of these different technologies work great together, which is pretty interesting from a Google Microsoft perspective. We use a lot of the Google visualization data science tools with the Microsoft tools. They're all based on a lot of Python, and those two groups work well. So depending on what you're standardized on, you can go with one versus the other, and it's very easy to move from one model to another model. A little bit about the back-end technology there.
Question.
Yeah.
So if one of the sensors gets knocked off, is there like a central hub that's listening?
The question was, is one of these sensors gets knocked off, how is that going to be handled? What's going to happen right there? Are we going to get an alert? And I think that brings up some context that probably I skipped over that's great to bring up. For immediate things that are happening, like something happened right now, either a sensor just immediately turned off, so maybe it's not working, or a sensor detected that all of a sudden vibration is through the roof. That is something we need to make an immediate action on. That's a great example for IoT where ARTS technology is going to go ahead and plug in there. If something goes just completely offline, how we handle that, we'll see that there's all of a sudden no data. That's probably a rules-based thing that says it's just not reporting anymore. Let's distribute that load across the rest of our inputs. And that's actually get into generalization, which we'll talk about in a little bit, will be helpful. Where the predictive side of it, we're going to talk about a predictive maintenance example. These turbines here, these are many, many millions of dollar investments. And we want to know that if we've got a maintenance cycle when we have to turn these things off or shut certain things down, maybe that's once every 3 months, once every 6 months, depending on the type of things that we're maintaining. That's where our predictive analytics is going to play. So one of these is real time. The second, as it's happening, one of these may be, you should do this maintenance, you should up it, because all the load the system's been under, it doesn't follow the traditional pattern. So I hope that helps to clear that up a little bit. Yep.
So I have two questions, right?
Mm-hmm.
One is related to data security. So the main concern that everybody has from the cloud standpoint is the security.
Gotcha. So two questions. The first question was around security. How do we handle that? And then about how do we scale these machine learning platforms. So the first one, security, as I mentioned, this platform right here, a lot of this platform was originally cloud-based, all cloud-based. Some of this had to come down on-prem due to some clients having that specific concern so that it can be controlled completely within their data centers. I would advocate that whether you're dealing with AWS, Microsoft Azure, the Google Cloud, they really are quite secure, and there's quite a bit of tooling that you can leverage to make sure that data is very well secured. Things like Key Vault, and then just good practices like using encryption at rest, encryption in motion, things of that nature. Certain industries, though, they're going to dictate, hey, look, this has to be here for whatever reason, and that's not necessarily an IT problem. That's more of a compliance concern or a business concern that we just have to honor and respect. Same thing with where we're deploying this, certain territories. Where can I store my data? It can't just all be in one centralized cloud spot. Maybe I've got to have deploy to a data center in the Asia Pacific, one in the US, and one in Germany. It all depends. So security is an interesting one, and I think that really goes back to the specific, I'd say, vertical that you're working with and the client you're working with. But there are technology tools like Key Vault that we can go ahead and leverage, data encryption at rest, encryption in motion, that I think mitigate that to a large degree. So if that answers the first one. The second one around scalability. So with TensorFlow, Google has got a package called Tensor Serving, which essentially is designed for serving up these AI agents built with TensorFlow, and that's a container-based approach. So containers will see a lot of these things. If you're dealing with Microsoft CNTK and you've built your own model using Cognitive Toolkit, and I say CNTK and Cognitive Toolkit, same thing. Microsoft's known for rebranding things quite often. They rebranded it that. You can use containers there as well, or you can also use Azure Web Roles to serve those up and scale that out in Azure if you're so inclined. And then with Azure ML, the scale is pretty much built for you by Microsoft, but your algorithms and your training sets are a bit limited. Now that's changing in future versions of Azure, but you can get started very quickly with Azure Machine Learning. And if you have things that there's services out there by IBM, Microsoft, Amazon for just standard cognitives like speech synthesis and things like that. If you can use that and don't have to build a model, why not? Your time to market can be months as opposed to a much longer cycle for a custom AI agent. Yep.
So how do you guys have more knowledge than GE in this field? I mean, is there data? Is there devices?
Great question. So the question was, how do we have more knowledge than GE? I would certainly say that GE has more knowledge on these individual devices, but it's orchestrating the system. That's what we're seeking to do right here. It's not just one device that we need to know a lot about. We need to know a lot about how all these influencers on that system, all right, may result in a predictive event. And it's not just one turbine that maybe we're dealing with right here from GE. It's then other vendors that are provided the distribution network. Then we've got all of the endpoint systems. And if we're in retail or financial services, maybe these are, as opposed to houses, we're taking the data the other way, and we're dealing with things like, I'm paying on my Apple phone or whatever, point of sale, back up through. So I wouldn't say it's about each individual specific device. Each one of those vendors is going to be the expert there. What we're advocating is to bring all of this together in an orchestrated fashion is the value that we might bring to the table. So, all right.
So you guys use like different cloud technologies to build a model, right?
We bring IP, all right, but I wouldn't say that we have a product that you're going to get in a box. We bring IP to the table, and we also have a good-sized team of data scientists on staff that have worked with these various technologies. So, I think as Christos mentioned, we've got a framework in how we deliver software, and team members that are experts in that, we do want to align to our clients, though. Especially when we're dealing with enterprise, there are certain compliance things and behaviors and things that they do. We want to be respectful of that. So we'll take the IP that we have, bring that to the table, and essentially customize that and modify that based on the specific needs of the client.
So you have any expertise in Zeppelin or Jupyter side of things?
So the question was, we had expertise in things like Jupyter. So what is Jupyter for everyone? It's essentially like a notebook. Think of it like Word, but you can embed code within that document. This is a great segue because I'm going to provide you guys with a Jupyter notebook that you can run the data science experiments I've got here as a takeaway that'll go ahead and train a couple of different models so you guys can kick the tires on it. Now, I'm not going to unpack that here for everyone because it'll probably get a little boring for some of the non-tech folks, but you guys will have that as a download that you can go ahead and run, and that is a Jupyter notebook. It'll take you literally 15 minutes to set up and run. I tested this on my wife, and she was able to get it running. She's a teacher, so I feel that was a pretty good, good litmus test right there. So Jupyter and tools like that gets back to what tools do data scientists use to figure out these models. Our data scientists are free to use, essentially, for the most part, what they want. We do want to align to what our clients have invested in, because we want their data scientists also and their teams to understand that. But once it goes through data science, we still have to operationalize this at scale, and that's where the data science and the engineering must go hand in hand. The data scientists are going to be great at creating that model, within a scope, but we need to scale that up, scale that out. And that's where the engineering team must also be involved. So we have a role we call data engineers. These are developers with probably a bit more math background than a traditional developer, and they are essentially the arbiters between the data science team and then the traditional build and development team. And then, of course, they're working with an overall team with DevOps and everything else, and all that rolls into it. So we talked a bit about our sensors right here. Really, the takeaway here is the giant data volume. So I'm going to move quickly through some of these just to make sure we're on track. These are daily data volumes that we might see. How the heck did I get to that, or am I making that up? These are some just rough assumptions on how we might get there. So these IoT devices, they generate very, very small amounts of data, but we're getting so much of that data volume adds up really, really quickly. In this instance right here, we're looking at about 2 gigabytes of data a day just with these somewhat arbitrary numbers that I plugged into this. The takeaway here is that if you're going to go the IoT path, you can get some amazing insights out of it. but be prepared for that data volume. There's a lot of data there you have to deal with, and you want to make sure you've got an appropriate pipeline. We could go ahead and use some big data things to map reduce this down into a much smaller data set that's perhaps more consumable. But the other option we have, and this is where Art's going to really unpack this for us, is we can do a lot of this work at the edge device. As opposed to pushing it all up into the cloud, let's do it at the edge of things, and that's where we can distribute that workload across all these various systems and actually reduce our overall infrastructure. So that's pretty much a win-win. So essentially, that's a bit about the data volumes we have right there. All right, so now I'm going to jump into machine learning specifically and just give a bit of a few definitions around that I just like to use. This slide is from NVIDIA. It's an old slide, but I love it. I give these guys some credit to it. And there's a lot of different ways people describe machine learning, artificial intelligence, and deep learning. And I don't know that they're all right or wrong, but for the sake of our dialogue, this is essentially what I'm using, and I'm always changing my thoughts on this. The bottom line is when people think of artificial intelligence, that's the superset of all of this. I think of general AI. That is, the stuff you see in science fiction with robots and people talking to things, and it's like human intelligence. We're nowhere near there yet. We're getting narrower and narrower, and what we're speaking about today is going to be machine learning, and that's all algorithmic approaches. It's math. It's all statistics and some calculus, all right? So it's equations that we're using to get down and solve these problems. Deep learning is a subset of that. That's where we're using artificial neural networks. The bottom line is a lot of these inputs we pass into these are going to be the same. And we're going to see these in a second as I unpack this. The algorithms behave different, but their job is to suss out all these inputs to a valuable output. And they do it in very different ways. And it's the computational power we need to solve this that really has made deep learning available to us today. And that's where the TensorFlow and the CNTKs come from. And that's where we can do things like look at a picture and determine whether that's a cat or a dog with AI. Never could do that before. And that's the algorithms and the thought around that is probably 15 years old in some areas. We never had the computational power to do that. We do now. The other reason is why would we do this? Why would we go to all this work? The main takeaway I have is generalization, I think is one of the biggest things. Now, not everything needs ML. If you've got something you can solve with rules, do it with rules. If you're trying to detect a problem in your accounting system and you see someone opens account and they've been deceased, well, that's a rule. You don't need ML for that. You know that a deceased person shouldn't open up an account. But if that was an arbitrary, probably not the best example, but generalization is where I think the real value comes in. And that's in traditional software, every input we have to program for. So if there's a new input that comes in, or new decision to be made, we have to program that. Someone has to engineer that decision. And when we have a few decisions, that's not too bad. When we have many decisions, 5, 10, or hundreds of thousands of decisions, that's not something that is tractable by a human, by a person. That's where these algorithms are great at this. We can pass in, here are all the inputs that got to this particular answer, let the math figure it out. The math will say, these inputs seem to influence this decision at this time, and that's a big part of data science, is that generalization. So that way, when brand new things come up that we never programmed for, we can still get valuable business information out of that machine learning. I'd say that's one of the biggest things we can do that it brings to the table is that generalization. And then, of course, there's problems we just can't solve with traditional software, speech recognition, computer vision, and that's because they've taken generalization to such a far step that it's sussing out things that are just too far beyond any person to program explicitly. So, to speak in generalization, I'm going to pull it up a little bit and talk about, everyone knows Uber Eats, right? Uber Eats is great. You go ahead and say, I want something from this restaurant, but I'm at a hotel. I go ahead and punch a few buttons, and someone delivers the food to me. So the example we've got here is imagine that we want to add machine learning to Uber Eats to predict what I want to eat. All right? And we're going to bring it back down to energy in a second with a much more sophisticated example. But this is essentially how we add machine learning and data science into traditional software. We're doing a regular Scrum development. That's great. Once the CEO says, hey, listen, I want to do predictive ordering for our customers, wonderful. Now there's another methodology. Crisp DM is what we use. Bit of a research methodology, but for you guys that are Scrum people, you won't feel any pain or know any difference, because with that data engineer I talked about, that's the interface layer, and this tooling is exactly the same. It's more so on the data scientists, how they operate, but it gives the business visibility into what we're doing. For a non-ML approach, I want to make a list of, maybe we may attack this by saying, what was ordered most recently, what was recommended on a price, what are the reviews. These are all a few things I've arbitrarily picked. If we have a few of them, I think we can engineer that. We can program that. No ML involved whatsoever. When we start getting more items, that's when this gets really tricky. That's when ML comes into play, and that's when we can use generalization to solve this for us and get better and better. And then if we're dealing with edge devices, it can start learning individuals, how individuals are working or what they're eating and requesting, and now it's tailored, if you will, to what you have ordered in the past. And how do we program this? Here's what we've got. Everything that we passed in here is what we call features. Those are the inputs on how we train these models, or these algorithms, I should say. Forget about what algorithm that is, because we can pick different ones. But in this case, we're looking at a multi-class prediction. Was the satisfaction high, low, or medium? I'm going to take some data that I've got that says day of the week, time of day, was it ordered recently, the distance, do they have a vegan option? Who knows? We can expand this out to as many possible things you can think of, and I'm going to say, here's the answer, the label, and then I may take some third-party data. Yelp, weather, who knows? Once I have all of this, I can now pass this into many different algorithms, and this is what the data scientist is going to do. In this case, we've just got 4 simple algorithms right here we may be evaluating. In truth, we'll use tools to evaluate hundreds or thousands of potential algorithms and see how they perform. And what we'll end up doing is saying, all right, one of these algorithms has performed better than all the others. We'll go ahead and take that, generate a model from it. Now that gets deployed up into the cloud or on-prem or wherever we want to operationalize it. Question, yep?
How did you know it performed better than the others?
So with all of these models right here, with the different types of models, these are multi-class predictions. So what we'll look at is something called the confusion matrix. Essentially, this will say, here was the predicted class, here was the actual class. So a predicted class would be, let me back that up. We'll take this data right here, and what we'll do is we'll split this out to like a partitioning scheme of like 80-20. So 80% of the data, we're going to go ahead and train our models with. We're going to hold back 20% of that, so that the models are never trained on that. They've never seen that, but we know the right answer. Then what we'll do is we'll run it through all these models, these algorithms, to generate the models, and then we'll throw at it the data we've never seen before, that the model has never seen before. How did that model do against that? Question?
So if you know the right answer, doesn't that introduce inherent bias into the model?
The question was, if we know the right answer, doesn't that introduce bias? Well, this is our training data. So this would be our labeled data that has all the right answers. We know there's a right. Now, bias is a great question, and that is that data influenced in some way that's subjective and not quantified? And that's really the job, I'd say, of our data scientists, to look at that data and determine if there's bias in there. But we hope that there's not. But that's a great point. If there is, we need to take a look at that. And that's a job, I'd say, of the data scientist and just some pragmatic reasoning to determine that. We've got a corpus of data that we have the answers to. This is our historical data that we're training on. We're training on past experiences, all right? But I'm not going to train that model on all the past experiences. I'm going to hold back a set of that none of the models have ever seen, and I'm going to see how they do on that data they've never seen before. If I ask them how they're going to perform on stuff they've seen, well, they should do well, but that's not really going to be informative that model is adding business value or that it generalizes well to new things. The inputs on how we're training this, it's all going to be classification. So this is all a multi-class. Yeah, so we could use something that's a neural network. We could use logistic regression to do all of that. The inputs into that model are going to be the same. Now, how we work with those algorithms are very different. The hyperparameters, all of those things. And the data volumes. If I've got small data volumes, a neural network might not be the right answer because it's not going to have enough information to suss out the appropriate weights. I might want to use something else. That's the job of data science, though, the data scientist. I am not a data scientist. But we have gotten to a point where we have a model in this hypothetical example right here. Now it's time to deploy this. This is where we'll go ahead and push this up into whatever deployment platform that we want to operationalize at. So if this could be Azure ML, it could be CNTK, it could be TensorFlow with tensor serving and containers. It makes no difference. The bottom line is, once this is up here running in the field, what happens is when someone wants to go ahead and predict where they want to eat, notice we don't know what the right answer is. We just pass in the same input data we had before that we trained with. There is no answer that we're giving it. It will come out with us and say, all right, based on this observation, it's high that you should go ahead and use this eat at this particular location. So we're taking all these locations right here and saying, which one of these should I eat at? And it's saying, let's see, observation, this one's 95 is, well, that's got a low, so we'll ignore it. We'll go to our first high, and it's number 1, which would be this particular spot, wherever that is. It's arbitrary, but that's how we would then score that and now tell the user where they should eat. Now, this model, when it's in the cloud, it's static. It's not being updated. We need DevOps to take all that information from the field, continue to evaluate this, and push it back up. So that's what we have to do there, and that's where Eric will speak to some of that. We've taken this whole thing that we just went through, and I've got this now in the context of turbine maintenance events, and this is where we have that takeaway data science experiment for you guys to have that actually looks at some data that's been, it's anonymized, that you guys can run through the Jupyter Notebook and see how all this comes out. And essentially what we're looking at right here is now IoT data that's coming in, and did we have a particular failure? And we're doing the exact same thing as we did before. But here we've got some more work to do. The data is not normalized right. The data is not distributed properly. This is the data scientist that's going to go ahead and make sure that that data set is structured appropriately for those algorithms to go ahead and do their work. So it's not, I did simplify things. It's a lot more work than that to make sure that we have appropriate distributions. And you'll see that inside of the little experiment that we go ahead and provide. We go ahead and get our models out of this. In this case, I have 2 examples. We pick the one that has a better ROC curve, and then we go ahead and operationalize just as we did before. And essentially, that's it. So that's data science right there. All right, we'll move into some IoT deep dive, and I'll be around. Thank you.
Okay, so I'm going to try in 15 minutes or less get you up to speed on IoT and what it is and what it's about. So what is IoT? It's those devices. It's your refrigerator that is telling you the milk is spoiled, so that deceased person won't try to open up an account because he looked and saw that if he had had an IoT device, he would not have, gone and opened up an account. Exactly. It really is, when you break it down, Internet of Things is the data and the thing. The things are the devices. And the devices talk to each other using languages. So I speak to my mother in English and I speak to her in Spanish sometimes. That's the language. Everybody's familiar with HTTP. MQTT is another language. And what that is letting things go back and forth. HTTP is one way. I listen to what mom says, but I don't do anything about it. MQTT, I'm moving data back and forth. I'm listening and I'm sending data back. So if I've got my turbine, I'm listening to data coming from the turbine, I'm sending data back. And then how do we transport that data? How do we get things going? We use Wi-Fi, and I'm actually going to pass around a few devices. That is a temperature, pressure, and humidity sensor. I got 4 of them. And that's sending data using the HTTP protocol. I'm sending data up to the cloud, and I'm going to start processing that data. And then here's a third one. And that one is a Microsoft device that I'm going to send data back and forth. And the fourth one is, Yeah, this device is used, that's just a battery. Yeah. And this is, the fourth device is a distance sensor. So how do these things talk? How does this all work? How does this flow? So we start with the devices. We've got a distance sensor, and it'll tell you the centimeters. We've got a couple of temperature and pressure sensors. They all go into the hub. And the hub is nothing more than a huge funnel where I pull that data into. Then I'm going to take that data and I'm going to use streaming analytics to kind of consolidate, to group that data. I don't need to know the temperature every second from that device. I need to know it every minute. I need to know it every hour. I need to know vibration every 20 minutes. So I can use analytics to group that data, and then from there I can send it to Data Lake. I can send it to Taylor so he can start doing some work on it. I can send it to Power BI, and I can throw some desktops out there. These devices are just basic temperature sensors. So let's bring this down into an energy discussion. So we have a turbine, and we're getting temperature data on that turbine. And we know that if that temperature goes above 207 degrees Fahrenheit, we have to shut it down because that $50 million turbine will turn into a pack of bricks. So how do we do that? Well, we use the IoT device. We send that data up to a hub that funnels it. We send it to data analytics, and we consolidate it. We send it to functions, and we do something with it, and then we talk back down to the device. That's great, but let's say we lost Wi-Fi. Let's say our network is bogged down. Now, instead of that transaction taking a few milliseconds, it took 3 seconds. And in those 3 seconds, our $50 million turbine turned into a pack of bricks. How do we fix that? Well, that's what IoT Edge is. It takes all that learning, all that hub, that function, and it puts it into a container, and it puts it, as they say, on the edge. Not over the cliff, but just right on the edge, right there with the devices. So I'll have all my devices connected to a central hub, and that hub will have my filters in it, it'll have streaming analytics, it'll have Azure Functions, and it'll determine that, hey, we need to shut that machine down, so I'm going to send a command down to it, shut it down, and then when I get Wi-Fi, I'll send that data back up to Azure, and if I have Wi-Fi, I'll still do it quickly on the device and then send the data back up. So now we've gone from a 1 second, 2 second time lapse to 20 milliseconds or to whatever that number is. Just greatly reduces the time. So what I want to actually show, let's see if I can do this. So one of those sensors is got a T1 under the name of it, and it should be telling you that it's 73 degrees. So if you blow on the T1 sensor, you should see the humidity go up and the temperature go up. If you put your finger on it, you'll see the temperature go up. Yeah, the blood alcohol level will go up as well. Yep, 74.5. So what that is doing is I've taken data from that device, sent it through the hub, sent it to analytics, and now I'm reading it. A very simple example, but extrapolate that out to 500 machines, and now I'm taking that, sending it to Taylor to do some machine learning on it, do some predictive maintenance. I'm finding out that, okay, as the temperature rises, when it gets to a certain point, I need to go replace those parts before that machine turns into a pack of bricks. Yes?
I assume you just use Wi-Fi. How do you secure this tunnel to send in the data?
The gateway is secure. There's secure keys that you send back and forth. So the devices can't talk to each other unless they have the right security going.
Registered device.
Right. And I don't want to actually show the security key because this is going to be on Facebook and then everybody will hack my device. One of the devices I've got, I'm going to send data back and forth to it. So if you look on the device right now, that MX chip, it should have said AgileThought on it. If you turn it over, it just should have said AgileThought on it.
It did.
Okay. And then I can say, it should have just said hello as well. So what we've done there is we've used MQTT to send data back and forth. So for instance, there's a device company called Atlas Scientific that makes sensors, and I've been talking to them about putting pH sensors in the Hudson River and figuring out the pH of the Hudson River. We all know it's acid, but you know, they actually want to they actually want to try to do it. So what we're going to do with that is we're going to use LORAN, which is radio frequencies, to a hub. That hub will actually have Wi-Fi, and that hub will connect. So that hub will take care of the connection issues, and between the device and the hub will just be radio. So here is the IoT suite, which does this at scale. So now I've got 25 different machines, devices hooked up, going through a hub, going through analytics, and showing you in a dashboard. I've got temperature data, I've got humidity, I've got alarms set that when the temperature hits a certain value, I can shut it down. And all this using the IoT suite and using all the things we've talked about, we can use provisioning, and because we're a gold partner, we can help get that provisioning done and do this at scale. And that kind of leads into Eric talking about, okay, so we've got the data, we've got the devices, we're moving data back and forth. How do we deploy this? How do we get this out there? How do we update the firmware on these devices? And that's where Eric will come in, and I will push it over to Eric.
That's some awesome stuff. So we talked about some great machine learning, IoT. That's some great technology stuff. So how do we get that out and operationalize that, right? So DevOps, I'm going to quickly go through DevOps and why we would operationalize these types of things. So we wouldn't use DevOps just for that. DevOps is really operationalizing software delivery. And what we're going to talk about real quickly is we want to use continuous delivery for DevOps. That's going to get your value. It's going to your customer quickly, consistently, and reliably. And we're going to be able to take these, the software that's running the IoT devices, push them out to, say, a larger region or a new territory. As long as we can scale that and get those applications out quickly and with lots of automated testing, we've got a good process. So kind of tying these all together, we want to have a team or a team member who can help you deploy all these applications out to your different environments. So real quickly, you know, how many DevOps engineers does it take to screw in a light bulb? Zero. They automated the process. Come on, people. Come on. What do you, they wrote a Puppet script for that. Are you kidding me? Nobody's buying DevOps. That's right. So anyway, I had another joke around the deceased person, but I was told not to tell that, so sorry about that. So moving on. Moving on, with DevOps, we're enabling consistent and reliable, high-quality deployments. So your typical process has biz, engineering, and ops kind of in separate areas. Obviously, with Agile, we've moved everything together. So when we talk about DevOps, we're talking about an Agile team that has DevOps as part of that. So DevOps is a cultural thing as part of that Agile movement. We're doing all these different tasks really within short feedback cycles, right? So we're planning, prioritizing, deploying and building, operating and releasing all within a sprint, really. So that's kind of the essence. If you're a Scrum team, you know that's kind of the essence of being able to deploy releasable software at the end of a sprint. So that's the kind of feedback cycles we're talking about. And also we're talking about feedback coming from automating, monitoring, and telemetry, those kinds of things. So this is kind of a nice graphic talking about how we prioritize things and how we get that out to production with automation and tooling. Some key concepts there, if you're not doing this, continuous delivery. Continuous delivery, that concept really originated with Jez Humble. If you haven't read the book, Continuous Delivery, it's a great book. There's also a great talk from Jez on Agile from the Agile Alliance in 2017. It's out there on the web. I highly recommend listening to that video. But really the concepts here are build automation. So you need a team member who can help out with build automation. That's part of that DevOps. Continuous testing. We talk about continuous integration, continuous testing. If you're not automating your testing, that's not going to help you have that reliable, high-quality deployment. So those have to be integrated in your delivery. And of course, your deployments need to be automated. So when we're talking about this, deploying new software upgrades to your IoT devices out to the cloud, that all has to be automated. And that's done through release automation. We use tools like VSTS, Release Manager is a tool, Puppet, Ansible has some. So there's a lot of tooling to help you automate that. Finally, intelligent environments. We're talking about configuration automation. We're talking about infrastructure as code. So you certainly want to have your DevOps role helping version your code, your infrastructure, the same way you would version your code, and those can be intelligently hooked together. You can roll back to the right versions of the environments in the code. Data seeding, that's something you need to make sure your data is working as well with your automation. And finally, the feedback loop. When we talk about monitoring, monitoring is more about your environments. Is our software up? Nowadays, we really want to know errors that are happening before our customer is aware of them. So we want to automate that, make sure we're using some tools that help with that. We use things like New Relic and Application Insights. And then you have things like telemetry. So telemetry is going to give you information about what your customer's actually using. So a lot of actionable data around that. So that's really kind of a real quick walk through how DevOps kind of brings this all together. Thanks a lot. Well, thank you, Eric.